continue on. We're talking, I don't know, chapter 13, maybe. That seems like the right chapter. We're talking chapter 13, which is obviously acids and bases. And remember that an acid really is anything that can produce H plus ions in solution, which are hydrogen ions. Also in sort of acid-base chemistry, it is also oftentimes referred to as H3O plus, which is the hydronium ion. They are used, as we talked about, sort of interchangeably, both in sort of equations and formulas as well. Bases are anything that has the ability to produce hydroxide. And once again, like we were talking about, that's the ability, again, to produce free hydroxides in solution, or the ability really to kind of produce free H pluses in solution. And that would really classify you as an acid, really, or a base, is the ability to do that production. A more sort of general definition of acid and base that most people think of is the Bronsted-Lowry definition. And in the Bronsted-Lowry definition, an acid is a proton donor. So again, that would obviously be something that gives away an H plus, while a base is a proton acceptor. And as we talked about last time, remember that the plus part there is really important because it does affect the overall charge of whoever has donated the H plus and whoever has basically accepted the H plus. So remember, a very common mistake is people will kind of just do something with the hydrogen, either take it on or take it or put it off, and forget about the charge. So the charges do sort of change. The relationship of sort of the Bronsted-Lowry relationship is we have an acid and we have a base. And on the other side, we have a conjugate acid and a conjugate base. And these are partners that are related to each other. And on one side, we have the acid. On the other side, its partner would be the conjugate base. And on one side there, we would have our base and our conjugate acid as the partner on the other side. Again, on the left-hand side of the arrow, the reactant side of the arrow is where we find our regular old acid and bases. Usually our conjugate partners are found on the right-hand side of the arrow on the product side. So that's where you find those guys. Remember that in this case, this is the Bronsted-Lowry definition, which means it's going to donate an H plus over there to the base. And that is also a really important thing because that can be the only difference between those two pairs, basically our partners, is a 1 H plus difference. And again, if it's more than 1 H plus or something else is different, they are technically not partners. Since the acid is donating its H plus, the conjugate base will actually have one less H plus. And since the base is accepting the H plus, its conjugate acid will actually have one more H plus as it goes across. Now, we also talked about the autoionization of water, which creates an equilibrium constant for water, which is known as Kw, which is the concentration of H plus times concentration of OH minus, and that equals 1 times 10 to the minus 14. Again, you can, as we talked about, use H3O plus here as well, same thing. We could use this if we know either the hydrogen ion concentration or the hydroxide concentration, and we could use it to compare. So again, if the H plus concentration is larger than the OH minus concentration, then the acid part is bigger than the base part, so it's going to be acidic. If the H plus concentration and the OH minus concentration actually equal each other, you will have a neutral solution, and they both will equal 1 times 10 to the minus 7 at that point in terms of the molarity. And if the H plus concentration is less than the OH minus concentration, then your base part of the solution is actually larger than your acid part, and we will end up with a basic solution at that point. You want to make sure, as we talked about, definitely use your exponent button here in these calculations. Otherwise, you will find yourself pretty far off. We talked about the pH scale, and that runs from 0 to 7 to 14. And remember, below 7, it is acidic. Above 7, it's basic. And 7 really is neutral because of this relationship here. And by the way, again, the relationship between H plus and OH minus is as one goes up, the other goes down. So sort of a opposite sort of relationship between those two concentrations. As you go from 7 towards 0, you're becoming more acidic. And as you go from 7 towards 14 there, you're becoming more basic in that case. You could calculate the pH of a solution. The pH tells you what you actually need, which is the hydrogen concentration, negative log of the H plus concentration. Once again, you could also use H3O plus in there as well if you like instead. We also talked about calculator wise. Again, if you have a display calculator, you're going to punch it in exactly the way it's written using your negative button, not your subtract button. If you have a non-display calculator, you got to go backwards on this one. You got to start with the number, hit log, and then hit the negative button. And again, if you're not sure, like we talked about last time, you hit log on your calculator and it does say log on the screen, then you do have a display calculator. And if you hit log and it says error, you have a non-display calculator. So that's again which way you go there. We also talked there at the end sort of a similar scale to pH, which is the POH, and that is negative log of the OH minus concentration. And we use that when we have, as the name implies, the hydroxide concentration. Now, again, the reason why we might want to use that is for a variety of reasons, but there is a really nice relationship that the pH plus the POH will equal 14. So again, if you're given the hydroxide concentration and want the pH, you get the POH and then take 14 minus it. Also really important, I think we talked about last time, which is you should probably always look at the pH value to determine if it's acidic, basic, or neutral. As we mentioned, there's just one answer again to that question. And again, very commonly people will calculate the pH and then the POH. And like I said before, kind of like, okay, this one's above 7, so it's basic, and this one's below 7, it's acidic. And again, they give it's acidic and basic for the same solution. So again, there should always be one answer on that. Most people have the pH scale in their head. Remember, the pH scale actually runs opposite of the pH scale. So if you have a high pH, you'll have a low POH and vice versa. And that's because of really this relationship here. We finished, I think, talking about that if you did have the pH value given to you, you can directly from the pH value, you can directly calculate the H plus concentration. And that is the inverse log of the negative pH. And again, on most people's calculators, when they do the inverse log, it usually will pop up a 10 and a caret. You want to go negative pH. Again, to get to inverse log on a lot of people's calculators, you just go like the shift button in the top left or the second button, and the log button usually is the one that you want to hit. You can also do pretty much a similar calculation here for POH. That can directly get you the OH minus concentration. And that's pretty much the exact same calculation, the inverse log of the negative POH, which again will give you a 10 and a caret POH here. So there is a variety of ways that you can kind of get some of these answers, and as long as you choose sort of a legitimate way, you should get really the same answer along the way. If you want to use KW, you can. If you want to do some inverse logs as pHs or POHs, that will work as well. In terms of significant figures with pH or POH type values, remember that your pH value or POH value should have the same number of decimal places as the number of significant figures in the concentration. So again, we're looking at significant figures to decimal places. And if you're going backwards from pH to concentration, you're looking at decimal places back to significant figures. So again, it's not sig figs to sig figs when we do it. It is sig figs to decimal places when we're doing those things. Any questions on any of that stuff we talked about last time there? All right, so I don't think we did any examples, so let's do some maybe, yeah. All right, the pH of rainwater is 4.82. Let's just make sure our calculator worked for everything. What is the H plus concentration? What is the OH minus concentration? What is the POH? And is this thing acidic, basic, or neutral? And on the bottom there, we have the hydroxide concentration. We want the pH. So for the bottom one, let's do the same thing. Make sure everything works. What is the pH? What's the POH for the bottom one? what is the H plus concentration, and again, is it acidic, basic, or neutral? Take a few moments, work through. All right, so let's take a look, see how you're doing. We'll start with the first one here. Since I asked you to basically find everything known to man, we will have many options as to what we could do first. Really, in this case, we are given the pH. So we got the pH there of 4.82. So because we are given the pH and we're looking for everything, we do have two options. We could obviously get the POH directly from it. We could also get the H plus concentration from it. So it depends which way you want to start. Just going to start with the POH. So the POH here would be 14 minus the pH, which would get us 4.82. And that's going to get us here 9.18, it looks like. At this point, again, we now have a couple of options. Now that we have the POH, we could get the OH minus from it. We also still have the pH that we could get the H plus. So I'm going to go with the H plus first. So again, the H plus concentration is going to equal the inverse log of the negative pH. Again, on your calculator, when you punch that in, probably a 10 and a caret, you want to go negative 4.82 and close parentheses. So once again, on most people's calculators, you probably should do something like this. If you have a display calculator, hit your second button, top left corner, or shift button, hit your log button, hit your negative button, and then punch in your pH there of 4.82. Again, if you have a non-display calculator, you need to actually punch in 4.82 first. You then need to make it negative by hitting the negative button. Then you need to do your second button or shift button and your log button. So again, depending on which calculator you got, you should do one of those two things. And if I do that on my calculator, which is neither of those, let me try this calculator here that has a dedicated button for it, negative 4.82, that is going to give me something with too many zeros to count at this late hour. That's going to give me an H plus concentration of 1.5 times 10 to the minus 5. This is molar. It does need a unit because it is a concentration. Now, at this point, again, we have a few options. Now that I have the H plus, I could go right into the KW if I want to do that way, or because I still have the POH, I could do the same calculation with the POH here. So I'll do that. The inverse log of the negative 9.18, which is our POH. Again, 10 caret negative 9.18. That's going to get me there, something, negative 9.18. It's going to get me a 6.6 times 10 to the negative 10 molar as my OH minus concentration. First off, any questions on that calculation is there? This solution is acidic, basic, or neutral, this one? That was not the trick question. It's acidic, basic, or neutral? It is acidic. Again, we want to look at the pH that was given to us. It's less than 7. Once again, you should not be circling all the options there. Yes, so just one answer for that. Any questions on any of that? Once again, like I said before, you could use the KW if you wanted to get the OH minus, just like we did previously. Again, really should give you the same answer. Might be slightly different with rounding, but it should be pretty darn close. By the way, we had 2 decimal places here, 2 significant figures here when we went back to concentration. So again, going backwards from like pH to concentration, you want to maintain decimal places to significant figures as well. Any questions on any of those there? All right, let's take a look at this one. This one, we have the OH minus concentration. So we could do, again, a variety of things since we do have the OH minus concentration given to us, which is 2.5 to the minus 7. We can get the H plus concentration using KW. We could also get the POH from it. So just to mix it up, I will go with the KW calculation here to get the H plus. So the H plus would be 1 times 10 to the minus 14 using KW divided by 2.7 times 10 to the minus 7. And that will get us here. Looks like 3.7 times 10 to the minus 8. Again, it needs molarity there as a concentration. Now, pretty much I could just go in with each of these. So I'll go into my POH here, which is my minus the log of the OH minus concentration. Going to give me minus the log here of 2.7 times 10 to the minus 7. And that's going to get me here. Yeah, it is like 2.5, and it's kind of like a 7 if you did it wrong. Thank you. Thank you. At least he caught me before I punched it in. Let's go back, delete. There we go. 2.5. Thank you. To the minus 7. And maybe punch it in right back, delete. Minus 7 would be good. There we go. All right. So I think I got all the right numbers there. 6.60, by the way. And at that point, to get the pH, you could plug in the H plus concentration, or you could take 14 minus the POH. So I'll just do that. Seems a little easier. Less numbers, maybe to punch into my calculator. Hope for the best. A little 7.4 action for our pH. Any questions on any of those calculations? Again, it does open up a variety of ways that you could get to these numbers. And like I said before, as long as you choose a legitimate way, it's all should get you the same end result. It doesn't really matter sort of which way you go. By the way, this is acidic, basic, neutral. This is, yeah, it's just slightly basic above 7, so slightly basic there. Again, we're rolling with 7 on the nose there for neutral, right? Any questions on any of those calculations there? Okay, again, I think punching into the calculator, most important thing. Let's do it all again here. Acid, basic, or neutral if we have an H plus concentration of 3.5 times 10 to the minus 6. So you have basically two options right out the gate here. You could again use Kw to get the hydroxide concentration. You could also obviously use the H plus concentration to get the pH. So I'm going to go that way first. I'm going to go pH is equal to negative log of the H plus concentration. I'm going to throw that in there carefully. 3.5 times 10 to the minus 6, I hope. And we will end up with negative log 3.5 to the minus 6. Looks like a 5.46 here as our pH. Again, at this point, I could really get the POH pretty simply by taking 14 minus my pH. So that would give me 14 minus 5.46. That's going to give me an 854 there, 8.54 as our POH. And at this point, like I said, however you want to get the H plus, if you want to do the H plus is our inverse log of the negative pH. You would then have something on your calculator that looks probably something like this before you hit enter. And that was 5.46. Actually, I don't want that high. I want the OH minus. Bad. I already have the H plus. Let me just solve for the H plus again just to make sure I did it right there. All right, try that eraser here. All right. We'll cut it out of the video later. It'll be all right. All right, so OH minus there. There you go. Inverse log of the negative POH here will get me my OH minus. So 10 to the negative 8.54 in this case. And that's going to get me negative 8.54. Looks like a 2.9 times 10 to the minus 9 molar. Alternatively, again, you could use Kw if you like, which obviously your OH minus would equal 1 times 10 to the minus 14 divided by your 3.5 times 10 to the minus 6. And again, it should basically get you back there as well. Any questions on any of those? Acidic, basic, or neutral, this one, by the way? It is acidic with a pH of 5.46, less than 7, yeah. Any questions on pH, POH, H plus, OH minus calculations? Clearly, you need to be able to obviously do those, yeah, and stuff. All right. So let's talk a little about acids and really bases as well. We'll talk a little bit about electrolytes and different types of electrolytes. So first off, electrolytes, as you may remember, are substances that when they go for a swim in water, they basically will break apart into ions, right? They'll produce positive ions and negative ions. Because they produce those ions in water, they are able to conduct electricity really well in some cases. They can still conduct electricity, maybe not so well. And there's non electrolytes that really don't conduct electricity. So, strong electrolytes will 100% break apart in solution. So if you have something that's a strong electrolyte, like a sodium chloride solution, in the sodium chloride solution, you pretty much have 100% of sodium ions floating around and chloride ions floating around. You pretty much got none of that still together. So if you were going to look at this, basically all you would see in this solution are ions basically floating around. No whole units still together. That is why it's considered a strong electrolyte because, frankly, you could think of it like this. It's a one-way street, basically. Everybody's going to dump out on the product side. Nobody's really coming back the other way. It's just going to completely fall apart and break apart and produce a lot of ions really quickly. Now, a weak electrolyte, on the other hand, is something that actually will stay together in solution, but will still break apart just a little bit. So different than a strong electrolyte, if you take something like acetic acid here that we have, this will actually be mainly what you have in solution. You will have a little of these ions that are produced. So when you look at a beaker of that, you would mainly have that acetic acid, for example, still together. But you will get a little bit of ions floating around, like some acetate, a little H plus ions floating around. So since it's able to still produce some ions in solution, it's considered a weak electrolyte. It will not conduct electricity as well as a strong electrolyte. So the common example when you talk about electrolytes is like a light bulb. So if you take some electrodes that's hooked to a light bulb, and you put it in a strong electrolyte solution, the light bulb will go off and shine really, really brightly because it's going to be able to conduct electricity really, really well. If you take that same sort of light bulb with electrodes and you put it in a weak electrolyte solution, the light bulb will turn on, but it'll be very, very dim, like almost like it's dying, but it will have enough to kind of turn on, but it'll be very, very dim. It's not conducting as much energy or conducting as much electricity. Now, when we talk about acids and bases, there are certain acids that are strong acids, and there's certain acids that are weak acids, and there's also strong bases and weak bases. One of the other main differences with a weak electrolyte is we typically see these arrows heading in both directions, and that's our equilibrium, right? Arrows that we see are reversible reaction, our forward direction, and our reverse direction happening. So something like HCl, nitric acid, perchloric acid, sulfuric acid, these are all strong acids. They all will essentially send an H plus over. And because we do have water in this equation, we will produce H3O plus and Cl minus. We'll form a little H3O plus and some nitrate. We'll form some H3O plus in this equation and some perchlorate and a little H3O plus, and actually in this case, a little hydrogen sulfate there in this case. So when we talk about strong acids, there's a list, and I think we'll see it in a second, but here's kind of the foolish list of it. We have our hydrochloric acid, we have our nitric acid, like we see down there. We got our perchloric acid, we got our sulfuric acid. We actually have our hydrobromic acid and hydroiodic acid. So those sort of 6 acids are pretty much considered strong acids. When they go in solution, they will 100% break apart. So if you took something like hydrochloric acid and you dumped some HCl in, you are pretty much only going to have ions floating around. And this is why it's considered a strong acid, because basically you just generated a bunch of H plus really, really quickly in that solution. All it has to do is go for a swim, and that solution is going to have a ton of free H plus floating around. It's going to make it really acidic because as the H plus concentration goes up, what happens to the pH? Goes down, right? So the higher the H plus concentration, the lower the pH we will have in that solution. Any questions on that there? You should know these six strong acids, and I say that because, frankly, if it's not one of those six, then you could pretty much make a pretty safe guess that it's a weak acid. So, by process of elimination, just knowing these six, you'll know if you come across something other acid that's not one of them, you'll know perhaps it's probably a weak acid. So that's a good thing to kind of know. Weak acids, on the other hand, are weak electrolytes, so they do mainly stay together. So as I was talking about there, they still will donate their H plus over. And in this case, we will still form H3O plus, and we'll have F minus. We will form H3O plus in this case since we have water in the equation, and we'll have NO2 minus. We will form H3O plus, and we will have a little sulfate action happening. And we will have H3O plus and hydroxide in this case here. So again, this is the way that you can represent this dissociation of an acid. As we talked about, you also, and it is correct to leave the water out if you want, and just write it like this, or like hydrofluoric acid. That is perfectly fine. It again is basically the exact same thing, both of those equations. Just like over here, when we were talking about HCl, you could leave the water out on the previous slide with HCl and just write it as this, which is H plus and Cl minus. So once again, this is a perfectly fine representation of what is going on with that strong acid, just like this is a perfectly fine representation of what's going on with that weak acid. Again, you don't necessarily, for acids, need to include the water in there. Different though, when we have this, we pretty much are going to mainly have all of these guys still in solution. So when we have something like hydrofluoric acid, you will mainly have, kind of like your acetic acid there, you'll mainly have the HF units sealed together, but again, you will produce a little H plus and F minus, so you have a little bit of ions in there. And again, that's what still makes it an acid. This is why it's a weaker acid, because it will mainly stay together, only produce a little bit of H plus, and nowhere near the amount of like H plus that would be produced from something like HCl, which is a strong acid. So again, that's the difference there. We also have strong bases, which are strong electrolytes. And as I might have mentioned last time or before, pretty much group 1 and group 2 on your periodic table there, if you combo those guys with some hydroxides, like start at lithium to sodium to potassium, make a right-hand turn to calcium, and really going down strontium and barium. These are a lot of these guys that are comboed with hydroxide are really strong bases. Again, the word alkaline means basic. So that's where we find a lot of our strong bases. Because they are strong bases, they're going to, again, 100% break apart. You will have 0% of the sodium hydroxide units still together in the solution. So if you dump some sodium hydroxide into your solution, you're just going to see ions floating around, and you will, much like a strong acid, produce a lot of free OH minus really quickly into that solution. And what that's going to do now is basically raise the amount of hydroxide. So as the hydroxide concentration goes up, the H plus concentration will go down, and the pH then will go up, right? Because you have more hydroxide. So you'll have a higher pH because of the amount of hydroxide that is present. Any questions on that there? Just like acids, we do have some weak bases, and this is an example. In this case, it's going to actually accept the H plus here in this case. We know that F minus in this case is going to act as a base because, frankly, it doesn't have a hydrogen to give, so it can't act as an acid in this case, right? So don't forget about common sense that if it needs an H plus to donate and it doesn't have one, it cannot really act as an acid in that case, right? So that will actually give us, which is very common, the acid it comes from, the HF, and that will produce our hydroxide, which essentially is what makes it a base. Here, same deal, our nitrite is going to accept the H plus over that way. That again is going to actually form the acid it comes from, which is nitrous acid. And by donating that H plus over, that's going to get us a really big parentheses there, but that's going to get us our OH minus being formed, which again is what makes it a base. So weak bases also are weak electrolytes. They also are reversible as well. Ammonia as well is another example of that. Ammonia plus some water. Again, the ammonia here will accept the H plus. It will make NH4 plus and some OH minus, or ammonium hydroxide if you put them together. In that particular case, again, the ability to produce that. Now, the conjugate base of a strong acid there is a relationship between acids and their conjugate base pairs. So, and it's really an important relationship that we will see later on in this chapter. And that is, for example, if you have a strong acid, its partner will be relatively weak. So, for example, if you have an acid, its partner is the conjugate base. And if your acid is a strong acid, its conjugate base partner will be relatively weak. And opposite of that is if you have a weak acid, its conjugate base partner will be relatively strong. And bases work the same way. So if you have a base and its conjugate acid, if you have a strong base, its conjugate acid will be relatively weak. And if you have a weak base, its conjugate acid will be relatively strong. What do we talk about when we talk about weak and strong? We will talk about it obviously in this class, but in certain cases, if you produce a strong conjugate acid or a strong conjugate base, it actually has the ability to react with water. Dare I say, that would be one right there. So this is a strong conjugate base that comes from HF, which is a weak acid. And really what it means is, as I just said, it has the ability to, because it's floating around in water, to actually start reacting with water. And what it will do is pretty much what we see right here. It has the ability to produce, for example, in this example, hydroxide. And because it has the ability to produce hydroxide, it has the ability to affect the pH of that solution by having the presence of that F minus in that solution. Same thing with a strong conjugate acid as well. It will have the ability to continue to react with water. Weak conjugate acids and weak conjugate bases lack that ability to react with water. These are types of reactions that we'll talk about in this chapter, which are known as hydrolysis reactions. They basically can react with water and produce either H plus or OH minus, and they can have an actual effect on the actual pH of that particular solution. And we'll obviously talk more about that in just a bit. H3O plus is the strongest acid that you could have. OH minus is the strongest base that you could have. By the way, when we talk about this being a strong conjugate acid or a strong conjugate base, just so there is no misunderstanding, this guy, which is a strong conjugate base, is still a weak base. It is nowhere as strong as sodium hydroxide, which is straight up just a strong base. So when we talk about it being sort of relatively strong, we're talking about in the sense of its ability to continue to react with water and produce something like hydroxide, but it is still a weak base overall. It's nowhere near as strong as a straight up strong base by itself. Any questions on that there? All right, we will lay it up there